everyone. In this video, I will be discussing scientific notation. It will be the 19th and last video in our series on arithmetic. In order to understand scientific notation, you will need some understanding of both exponents and decimals. If you need to brush up, then here are some recommended videos. Video number 8, Powers and Roots. Video number 14, Introduction to Decimals. Video number 15, Multiplication and Division of Decimals. Video number 18, Rules for Powers. With the creation of the first telescope in 1608 and the first microscope in 1609, science began to look at objects that were very small, very numerous, or very far away. Without scientific notation, working with these numbers can be quite awkward and difficult. Let me give you an example from chemistry. Don't worry too much if you are unfamiliar or rusty with the chemistry that I will be discussing. I'm just trying to give you a feeling for the mathematics involved with this branch of science, and hopefully, a small appreciation for the science itself. First, let me give you a little chemistry background. Chemists began to study the composition of substances in earnest in the early 1800s. Over the course of many years, at least 90 naturally occurring elements have been identified. I say at least 90 since, even today, there is no universal consensus as to whether other elements, which have been created in a lab, actually exist in nature. It is agreed, though, that if they do, they are exceedingly rare and exceedingly short-lived. Everything on Earth is comprised of some combination of these naturally occurring elements. The smallest unit of these elements is called an atom. Each molecule of water, for instance, is composed of 2 atoms of hydrogen for each atom of oxygen. It is the familiar H2O. Many of us remember a bit about atoms from our high school days. The center of the atom is called the nucleus. The nucleus is essentially all of the mass, or weight, of the atom. In the simplest terms, the nucleus is made up of 2 types of particles, protons and neutrons. The number of protons in the nucleus determines the kind of element the atom is. Neutrons help stabilize the nucleus. Neutrons and protons have nearly identical masses and, for our purposes, both have a mass of 1 atomic mass unit. A small change in the number of protons in the nucleus not only changes the element, but dramatically changes the characteristics of the element. For instance, hydrogen, whose chemical symbol is H, is an explosive gas which has 1 proton in the nucleus. Hydrogen usually has no neutrons, so its atomic weight is about 1 atomic mass unit. Helium, chemical symbol He, is a very stable gas with 2 protons in the nucleus. It generally has 2 neutrons as well, so its atomic mass is about 4 atomic mass units. Gold, symbol Au, has 79 protons in the nucleus. It nearly always has 118 neutrons, so its mass is about 197 atomic mass units. Add 1 more proton to the nucleus and you get mercury instead of gold. Mercury, symbol Hg, is a toxic, heavy liquid under normal conditions. Oxygen, symbol O, is the 3rd most abundant element in the world. All the oxygen nuclei are made up of 8 protons, and nearly all have 8 neutrons, for a total of 16 atomic mass units. Atomic mass units are useful in comparing the relative mass or weights of atoms, but the problem is that an atomic mass unit is way, way too small for us to easily measure. So, from a practical standpoint, we need another way of measuring these elements. To solve this problem, chemists introduced the notion of the gram atomic weight of an element. It is simply the atomic mass of the element in grams. Therefore, the gram atomic weight of oxygen is 16 grams, the gram atomic weight of hydrogen is 1 gram, and the gram atomic weight of gold is 197 grams, and so on. Now we have something we can measure in a laboratory. The gram atomic weight of any element is called a mole of that element. A mole of oxygen is 16 grams, a mole of hydrogen is 1 gram, and a mole of gold is 197 grams. In chemistry, a mole is used in a similar manner to cooking. When we cook rice, we often use 2 cups of water per cup of rice. We don't count the drops of water, and we don't count the grains of rice. So 2 moles of hydrogen and 1 mole of oxygen means that we have the right ratio of hydrogen and oxygen to produce water. But how many atoms make up a mole? The answer is a number called Avogadro's number. Here is Avogadro's number to the first 4 digits of accuracy. There are this many atoms in 1 mole. Avogadro's number was originally estimated in 1865 and has been refined several times since. It is an important number in chemistry, but, as you can imagine, it is an extremely difficult number to use in calculations in this form. It is simply too large. Let me give you another measurement from chemistry. The diameter of an oxygen nucleus is this. Again, a very difficult number to work with in this form. It is simply too small. This is where scientific notation comes in. Scientific notation allows us to write these very large and very small numbers much more easily and to simplify the use of arithmetic operations on these numbers. Scientific notation is simply an application of what we know about exponents or powers. Let's look at the powers of 10 and apply it to very large numbers. 10 to the 0 power is 1. 10 to the first power is 10. 10 to the second power is 10 times 10, or 100. 10 to the third power is 10 times 10 times 10, which is 1,000. 10 to the fourth power is 10,000. 10 to the fifth power is 100,000. 10 to the sixth power is 1,000,000, etc. 2 things are important to note. The first is that with the powers of 10, the exponent is the same as the number of zeros in the number. 1,000,000 is 1 followed by 6 zeros, and is also 10 to the sixth power. Secondly, I can write any positive integer as the product of a real number and a power of 10. By convention, in scientific notation, the restriction on the real number is that it must be greater than or equal to 1, but less than 10. The real number is called a significand, or sometimes mantissa. The power of 10 is called the exponent. For instance, I can write 237,000 as 2.37 times 100,000, or, much more usefully, as 2.37 times 10 to the fifth power. 2.37 is the significand, or mantissa, and the exponent is 5. It is relatively easy to express large numbers in scientific notation. The significand is the digits I have before the continuous string of zeros. An easy way to figure out the exponent is to count the number of places I would have to move the decimal to get a significand greater than or equal to 1, but less than 10. Take a moment to try this. For the number 50,320,000,000, what is the significand and what is the exponent? Pause the video while you work this out, and then resume the video once you're done. In this problem, the significand is 5.032. Those are the digits in front of the continuous string of zeros, and 5.032 is between 1 and 10. I had to move the decimal 10 places over to get 5.032. So the number 50,320,000,000 can be written as follows. How did you do?
Nailed it!
Great. The importance is that I can write very large numbers like Avogadro's number much more easily, and the result is much more understandable to you. In the case of Avogadro's number, 6.022 is the significand. I must move the decimal point 23 places in order to get 6.022. So Avogadro's number is written as 6.022 times 10 to the 23rd power. Over the years, the notation we use for scientific notation has changed. When I was a young student typing out math papers using a manual typewriter, yes, I am that old, it was quite tedious to try to type the superscript exponent. Over time, different groups of people who used scientific notation frequently developed notations which allowed the notation to be typewriter and keyboard friendly. The bad news is that there are a few different notations out there. Scientific notation is not completely standardized. The good news is that they are all pretty easy to figure out. Probably the most common notation is to write the significand followed by a capital E for exponent, and then the value of the exponent, using either a plus or minus sign to signify whether the exponent is a positive or negative number. Since in scientific notation we always use a base of 10, it is unnecessary to include that in the notation. Here we have a common scientific notation for Avogadro's number. Using scientific notation means that I can perform multiplication and division on very large numbers much more easily using the rules associated with exponents. Let's try a problem. There's an old saying, for all the gold in Fort Knox. I don't like beets, so for me the saying might go something like this. I wouldn't eat a plate of beets for all the gold in Fort Knox. Suppose we wanted to calculate how many atoms of gold are in Fort Knox. Here are the facts that we need to do this calculation. In March 2020, there were 147,400,000 troy ounces of gold in Fort Knox. 1 troy ounce equals 31.10 grams. As stated earlier, 1 mole of gold weighs 197.0 grams. And of course, we need Avogadro's number, which gives us the number of atoms in a mole. These measurements can be expressed much more precisely than I have shown here, including Avogadro's number. But since we're not interested in being extremely precise, I've rounded off these numbers to make them easier to work with. Let's build this equation. The amount of gold in Fort Knox is measured in troy ounces. The weight of a mole of gold is in grams, so we need an expression which converts troy ounces to grams. Here it is. The gram molecular weight of gold allows me to convert grams of gold to moles of gold. The total number of gold atoms is found by multiplying the number of moles by the number of atoms per mole, that is, Avogadro's number. It would frankly be ridiculous to try and solve this problem without using scientific notation. I can't even communicate the solution to you in a meaningful manner without scientific notation. Life is short, so let's take advantage of what we have learned. My first step is to convert all the numbers to scientific notation. Here we go. 147,400,000 is 1.474 times 10 to the 8th power. 31.10 grams is 3.110 times 10 to the 1st power. 197.0 is 1.970 times 10 to the 2nd power. As previously stated, Avogadro's number is 6.022 times 10 to the 23rd power. I first deal with the significans. 1.474 times 3.110 times 6.022 divided by 1.970 gives me 14.01, rounded to 4 digits. Now I deal with the exponents. Recall that for multiplication I simply add the exponents, and for division I simply subtract the exponents. So 8 plus 1 plus 23 minus 2 is 30. My answer is 14.01 times 10 to the 30th power. We have an answer, but we aren't quite done yet. As I mentioned earlier, by convention, in scientific notation, the significand is a number between 1 and 10, inclusive of 1, but not inclusive of 10. My significand is over 10 right now, so I must tweak my answer a little bit to conform to this convention. 14.01 is equal to 1.401 times 10 to the 1st power. 10 to the 1st power times 10 to the 30th power is 10 to the 31st power. I have my answer. 1.401 times 10 to the 31st power. To perhaps give a perspective on the magnitude of this number, there are estimated to be more stars in the universe than there are grains of sand on the Earth. And there are about 10 million times more atoms of gold in Fort Knox than there are stars in the universe. By the way, I did a quick calculation of the value of the gold in Fort Knox. It is worth about $267 billion. The plate of beets is starting to sound more appetizing. Maybe I would eat it for all the gold in Fort Knox. So much for very large numbers. How about if the numbers are very small? In these cases, the negative exponents of 10 are helpful. Let's look at the powers of 10 again. Let me drop the larger numbers to give myself some room on the screen, and let's fill in the smaller numbers. There is a pattern that develops which is easiest to see when I express the fractions as decimals. 10 to the minus 1 power is 1 over 10, or 0.1. 10 to the minus 2 power is 1 over 10 squared, or 1 over 100. That is 0.01 as a decimal. 10 to the minus 3 power is 1 over 10 cubed, or 1 over 1,000. That is 0.001 as a decimal. 10 to the minus 4 power is 1 over 10,000. 10 to the minus 5th power is 1 over 100,000. 10 to the minus 6th power is 1 over 1 million. I can continue this indefinitely, but you can see a pattern emerging. The negative exponent of 10 is the number of places you would have to move the decimal point in order to get the 1 in the ones place. That is, the first place to the left of the decimal. In a similar manner to what we did with very large numbers, very small numbers can be written as a combination of a real number between 1 and 10, again inclusive of 1, times a power of 10. So 0.00047 is written in scientific notation as 4.7 times 10 to the minus 4 power. That is, I would have to move the decimal 4 places to the right to get 4.7. I mentioned earlier that the diameter of an oxygen nucleus in meters is as follows. How do I write this in scientific notation? The significand is 1.4, and I had to move the decimal 14 places to the right to get 1.4. So that becomes the value of the negative exponent of 10. In scientific notation, the diameter of an oxygen nucleus is 1.4 times 10 to the minus 14 meters. Let's do a little arithmetic with very small numbers. How close are we to being able to see a single oxygen nucleus? I looked on the internet and discovered that humans can distinguish something which is about 1 times 10 to the minus 4th meters, or about the thickness of a single strand of hair. With a light microscope, that is the regular microscope we're familiar with, we can see things which are about 5 times 10 to the minus 7 meters. How about by using an electron microscope? It is the most powerful microscope invented. I learned on the internet that an electron microscope can see objects as small as 5 times 10 to the minus 11th meters. Notice that with scientific notation, I can get a general sense of things very quickly. I can arrange the numbers in order based on the exponents, largest number to smallest. Between our naked eye and the oxygen nucleus, there is a difference between the exponents of 10. That means that the oxygen nucleus is about 10 to the 10th power, or 10 billion times too small to see. Even with the electron microscope, the difference in the exponents is 3, which means that it is about 1,000 times too small to see. Often a quick inspection like that is sufficient to answer our questions. A drawback of scientific notation is that it struggles when numbers are added and subtracted. Fortunately, in real life, it is rare that these calculations need to be done, but we should talk about it a little bit. You can only add or subtract numbers in scientific notation when the exponents are the same. For instance, 276,000 is 2.76 times 10 to the 5th in scientific notation. 5,000 is 5 times 10 to the 3rd in scientific notation. To add these numbers together, I must match the exponents. The easiest way to do that is to take 5 times 10 to the 3rd and move the decimal point in the significand 2 places to the left, thus increasing the exponent by 2 from 3 to 5. Now 5,000 is expressed as 0.05 times 10 to the 5th. The exponents match, and I can add the significands as I would normally add two real numbers. 2.76 plus 0.05 equals 2.81. I keep the exponent of 5. The answer is 2.81 times 10 to the 5th power. When adding or subtracting in scientific notation, we must also consider precision. I just looked up the national debt. It turns out there is a website where you can look at the national debt in real time. When I looked, the national debt was just a hair over $29 trillion. I took out my stopwatch and timed how long it took for the national debt to increase by $1 million, which was, frankly, a very depressing exercise. It was about 40 seconds. Here's the number in scientific notation to 4 digits of precision. What it means is that we can't really talk about the national debt with any kind of precision below about $10 billion. It is simply changing too fast. So, for example, We would not normally try to add or subtract something as small as $2 billion to something the size of the national debt. The national debt, as I've expressed it here, is to the nearest $10 billion. If I try to be more precise, I become less accurate. That is, the value that I give you is outdated almost as soon as I give it to you. Therefore, my increased precision is of no particular value to either of us. It is a waste of effort, at best. In a less depressing analogy, let's go back to preparing a rice dish using a cup of rice and 2 cups of water. Suppose in mixing the ingredients, I accidentally spill 5 or 6 grains of rice, or a couple drops of water. Is that going to make any difference to the quality of my rice dish? Of course not. The few grains of rice and the few drops of water are insignificant in comparison to the cups of rice and water, so adding or subtracting that insignificant amount is not going to change anything. When we use very large or very small numbers, we often encounter the situation where any addition or subtraction becomes insignificant and often meaningless. This ends our series of videos on arithmetic. It is my sincere pleasure and honor to have created these videos, and my sincere hope that they are useful to the viewer. Have a great day, everyone.
We hope to see you at Veterans Upward Bound very soon, and recommend a friend.